Okay, welcome everyone to session 2 of the June 2024 Python tutorial. My name is Jamika Marshall, and I'm so very pleased to welcome you all to this second session. I'd like to quickly allow our mentors to introduce themselves before we move into our first section today, which is going to be our first astrophysics background led by Geronimo. So Geronimo, I see you first in my window, so please give a quick introduction.
Sure thing. Hi, everyone. I said hi to some of you guys yesterday, but here I am again today. My name is Geronimo. You can call me Jero, Hero. I speak Spanish, so originally the pronunciation should be something like Hero. So that works. And yeah, I am currently a master's student on a program in astrophysics and space science in France. Currently, I am doing finishing my first year here in France, and very excited. I come from a background of an astronomy bachelor's program in Colombia. I am originally from the country of Colombia, and yeah, I am very excited to be here with you all, and I'll give you a very brief astronomical context today about some of the concepts that will prove useful for applying them into the notebooks and the activities you have later. So yeah.
Thank you, Geronimo. Philip.
Hi, my name's Philip. I'm a graduate student at Ashoka University in India. I don't actually work on astronomy. I work in a completely different field. I work in the study of infectious diseases, but it also uses a lot of coding, and I'm very interested in astronomy, at least at the amateur scale. So yeah, I've been associated with the PyaR program from 2018, though I haven't been doing work consecutively through the years. But yeah, it's a lot of fun to do this. I keep coming back.
So glad to have you, Philip. Okay, Madeline.
Hi, everyone. I wasn't here yesterday, but I'll be guiding you through the notebooks today. My name is Madeline. I'm a fourth-year PhD student in astronomy and astrophysics, and what I study is exoplanets, which are planets around other stars.
Wonderful. Thank you, Madeline. And our CREST founder, PyaR founder of everything, Raja Kurtha. Raja.
Thank you, Jamika. It sounds like I need a drum roll or something, the way you introduced me. Maddie, I did my best attempt at introducing you yesterday, but you did a much better job. So it's been my pleasure to work with the team here and pleasure to be part of this Python and research thing. We started this, a couple of my PhD students and I started this over 10 years ago as an in-person tutorial in an all-girls school in Palo Alto at Castellea School. There may be some Castellea students on this call today. And then we sort of transitioned it to an online tutorial in 2018. As Philip said, in November 2018, we offered this for the first time completely online, and it's evolved quite a lot since then in a positive direction, using Slack and Zoom and to really bring this content to all of you. I'm a professor of astronomy and astrophysics. I've been at UC Santa Cruz for a long time. It's going to be completing 30 years this year. And really been a privilege to work with all of you, with Jamika, with Hero, Philip, Maddie, Anand, and Lindsay as well, who are on this call on different aspects of CREST. All right, back to you, Jamika.
Thank you, Raja. And we have our other mentor who wasn't quite here when I first started. He probably came in and I didn't see him once we were doing the introductions, and that is Aparajito. Aparajito, welcome.
Hi everyone. Sorry, I lost the Zoom link, so yeah, took me a while, but yeah, I'm here now. I'm getting set up to complete Notebook 2. In the meantime, if anybody has any questions, please post them to the Slack channel. Yeah.
Wonderful. Could you give a quick introduction, a little bit of background about yourself to those who may not have been here yesterday?
Yes. turn on camera. Here we go. Yeah. Hi everyone. I'm Aprajito. I completed my master's in physics from St. Xavier's College, Kolkata, which is Raja's alma mater, and I've been mentoring for PyaR since 2021. And I've also been working with Raja on a research project since around that time. And I'll be the primary mentor for ASTF5. So, yep. For the SIP interns who are here. Yeah, hello everyone. Great to see you today. It's good to see so many of you back here. Most of you are here from yesterday, I believe. Okay, if anybody has any questions about yesterday's session, day one is usually heavy on the basics of Python. And we went over the different, we went over the very basics of Jupyter notebooks, why they are great for learning Python, the advantages of using Python as a programming language. By the way, I hope my audio is all right. My audio levels are all right. Yeah.
Yes.
Okay, so we went over the very basics of Python, how to run code, the basics of Python syntax, the different data types, and we learned a bit about user-defined functions. We learned about if-else statements, and we had to skip over the for loop section, the loops section. Has anybody here tried going over that section and looking into what loops are? Does anybody have any questions about that? Or does anybody need a quick, overview of loops? We can do that. We can do that very quickly. Please feel free to sound off in the chat. Meanwhile, let me share my screen. Show you first notebook. Sorry, the second notebook. Okay, hope everybody can see my Chrome window. Right. So somebody said, yes, please. I'm guessing they want a quick overview of the loops. Okay, great. So we'll do that. Let me run all the cells. Run. So we learned the print command. We learned about lists. We learned about strings. And we learned that lists are basically collections of objects. I'm using the term object a bit vaguely. Object has a very specific meaning in Python, but it's basically a collection of elements, right? These elements can be anything. These elements can be numbers, or these elements can be strings, characters, like single character strings. They can be integers or floating point numbers. In fact, they can be entire lists in and of themselves, right? So lists are very versatile, but they're not optimized for using with numbers. For that, we need something called a NumPy array, which Philip covered yesterday. Philip went over why arrays are necessary, why arrays are different than loops. Sorry, why arrays are different than lists. Line numbers. Come on. There we go. Okay. So we learned about if-else statements, right? If-else statements are basically when you tell the computer to make a decision using some Boolean variables. And oh, cool. Yesterday's recording is up. Thank you, Jamika. Yeah, I didn't think it would be available that quickly. Great. So everybody go check it out if you have missed yesterday's session. Not right now, obviously. Anyway. Sorry, everyone. My power is being a bit weak. If I cut off, please just let me know. Anyway, so we learned about if-else statements where we ask the computer to make a decision. More specifically, we ask the computer to make a decision only once. With the if-else statement, we learned about Boolean variables and how to use them in if-else statements. Now let us look at loops, right? We have already also learned about user-defined functions. User-defined functions are basically when you want to do a complicated operation and you don't want to write the same block of code over and over again, right? Because that's inconvenient. And if you make a mistake there in the formula, you have to go back and change every single instance of that formula throughout, right? So you do something called a user-defined function. And you can just, use the function as many times as you want. Once you have defined it and once you run that section of code, you can just use that function as many times as you want throughout the body of your code. And if you need to make a change, you can just make that change in the function itself. The change will be reflected throughout the script. So what if you want to repeat the same thing, not in different places across your script, but but consecutively in one section of your code, right? What if you want to do the same thing, say 10 times or 100 times, one after the other, right? In the same segment of the code. So that's where loops come. I'm going to skip over while loops because we don't usually use those. So let's do something called a for loop. I have defined something called, let me zoom in a little so that everybody can see clearly. I hope this is better. Right. Okay. So to create a for loop, you need some kind of collection. Okay. Here the collection is a list. We can see that it is a list of 4 numbers. And the for loop syntax is defined like this: for a certain placeholder variable, okay? Placeholder variable k in the collection, okay? Colon, next block will be indented with a space or a tab, and then whatever you write within this indented block will be repeated as many times as there are elements in this collection. Okay, let's run it and see what happens. So the loop just is supposed to go over this list, take every single element, okay, from that list, where k is the placeholder variable, k is the placeholder variable for every single element in the list, and then it just prints, okay? And every time the loop runs, you can see that it automatically creates a new line, and it prints k, right? And the value of k changes as the loop runs. And once the list is exhausted, once the collection is exhausted, the loop just stops, okay? For a for loop. A while loop is different, you need an exit condition for that, but we're not getting into it. So once again, the indentation block is very important, just like if-else statements. Again, once you have ended that indented block, okay, once you have shifted back to the left, once you have stopped using the indentation of space or tab, the code will proceed as usual, right? As you can see, the loop is basically the equivalent of writing print k square brackets 0, close square brackets, print k square brackets 1, print k square brackets 2, and so, right, in separate lines. That's the equivalent of it. And we can just compress that into this 2 elegant lines of code, right? So that's the beauty of a loop. You can do this with 100 elements. You can do this with 1,000. Loops are very handy. You can put a loop inside a loop. Okay, so I won't go over too much detail. You can see that we have to use 2 different placeholder variables, or Python will get confused. We have used something called a range. A range is a function that's also a collection. Okay. Let's see what range looks like. Range, let's do 4. Okay. Sorry. That didn't work, right? So let's convert the range into a list. Big go. So once you write range, range is basically a function that generates a collection starting from 0 to the number you listed, but excluding the number. So right before that number with an interval of, okay? That's with 1 argument. If you use 2 arguments, say 1, 4, it starts at the first argument and ends right before the second argument. Once again, with the default step of 1. And you can actually define the step size with the third argument. So, oops. That'd be better than issue. Oh. Sorry, filament. Does anybody remember how to define a non-integral step for the range function? Now I'll just do 10 and 2. So you can see that it starts at 1, it ends before 10, and it takes a step of 2. So it doesn't go from 1 to 2, 2 to 3, 3 to 4, but it goes from 1 to 3, 3 to 5, and so on. All right. So that's what range is. It is literally just a collection. If it's possible. Okay, we have a question in chat. If it's possible that instead of K or L, look for a certain number from my post. For example, 2 in my list. Yeah, okay, please clarify your question. And Philip will respond. Sorry. Okay, so that's what range is, in case you're wondering. And you can use range to define these loops very easily. And you can create an outer loop and an inner loop. So the inner loop will run completely for every iteration of the outer loop, right? So this is the result that would produce. Anyway, that's loops. A quick overview. If you have any questions, please post them to the Slack. Anyway, back to notebook 2. Philip covered the basics of NumPy arrays. NumPy arrays look like lists, but they're not lists. They are optimized for numbers. They are optimized for fast processing. You can actually multiply, scale it to them, a single number, to a whole NumPy array. You can't do that with a list. If you do, it will just concatenate the list that many times. NumPy arrays are optimized for that kind of calculations, and they do it much faster. If you want to do that with a list, you will have to run loops, which is obviously more lines of code, and it is inefficient. It's not faster, and there's more chances of making a mistake. So a range is much like what we just learned. It is much like a range. Okay, so 0 to 100 with step of 0.6. This is the array that Philip generated yesterday, or a variation of this. And once you have generated the array and named it, say, X, you can actually do a whole operation on it, mathematical operation on it. You can just divide it by 10, and then every single element will be divided by 10, and it will return an array with those elements, okay? It's lightning fast and it's very, very efficient. Okay. NumPy also comes with very helpful mathematical functions. These are very basic functions. We'll be using here a sine function and a cosine function. And even, once again, just put in x by 10 as an argument, and define two new arrays, y1 and y2. And then we can get straight to plotting. So plotting or data visualization is very, very important in science, right? Because like we saw with the paper yesterday, there were lots of figures in the paper. A plot is a very efficient way to express a lot of information in a small space, to express a diverse set of data in a small space, to express various relationships among the data, within the data, and to the thing that we use plots quite often for in our research is just to test our work, right? Sometimes we want to know that everything is running properly, and that you expect certain relations between some of your variables. You can just do a quick plot. If it doesn't look right, something is wrong within the code. So we are making plots every day, almost every day during our research. Even if those plots don't make it to a paper, you can make simple plots all the time. And the library or the package that is used most often for this plotting, by the way, package or library is just a collection of functions in Python. External collection that you can download and install. There are many packages. So the most common package is for plotting is something called matplotlib. If the name sounds a bit familiar to you, that's because it is a package that is specifically built to be consistent, somewhat consistent with the MATLAB's plotting syntax. That's where the name comes from. And it's been around for like 20 years at this point. It is the oldest standard plotting library of Python. And newer, faster, lighter packages also kind of depend on this in many ways. So you should learn about this package and how to use it. So plotting.
Sorry to interrupt. Yes. A few people are saying that it's slightly hard to understand you. Others in the chat are saying it's fine. So it could be an issue on their end. But if you could raise your volume a little bit, if that's possible, that may be helpful. Thank you.
Let me quickly go into the settings.
Yes, and I can hear you fine as well. People are saying they can hear you fine. I can also, but we know that all devices are not created equally, and I know sometimes my volume can change on its own sometimes, so it could be that. So thank you.
My volume is maxed out, unfortunately. My mic volume is maxed out, so sorry, but yeah, I hope it comes through clearly in the recording. If you are really, really having trouble, please look back at the recording. Yeah, I can't increase the volume, unfortunately. Anyway, sorry, my voice is a bit messed up today. Anyway, so how do we plot? This is a very basic plotting go, right? The plot function is the easiest way to make 2D plots, two-dimensional plots. The first argument is the variable that you want to put on the x-axis. The second argument is the variable that you put on the y-axis. And these are the only two necessary arguments for the function in matplotlib. Okay, you can see that we imported package pyplot from within matplotlib and called it PLT. Okay, and we did the same with NumPy. We called it NP, right? So all the functions that you see here, to start with NP dot NumPy functions, all the functions that you see here that start with PLT dot are matplotlib.pyplot functions. Okay, that's how you import efficiently. That's how you import without losing track of the functions, because sometimes sometimes different packages use the same functions, or like different functions with the same name. And if you import both of them, one will just replace the other. So you want to separate them like this. Anyway, then we have optional arguments, something called label. This label will determine what goes on in the key. We can define the color of the line. We can define the width of the line. We can define the style of the line. All of these are optional. If you want to know more about the visuals, please go over to the Slack space. There's a bookmarked link about matplotlib visualizations in the general channel. I bookmarked it. Join the Slack space. Anyway, we do the same with y2, and then we can set the limit of the y-axis, or the span of the y-axis that will be displayed in our plot with these two arguments. This is the lower limit of the axis, and this is the upper limit of the y-axis. We used the function legend to create this key, and we use xlabel to label the x-axis, and we use ylabel to label the y-axis. Let's run it. It takes a second for me. Oh, what happened? Okay, here we go. Great, and it creates this figure, all right? Can change, say, the limits. I can change the color. And it's gonna look like this, okay? So you can tweak around with the visuals, do what you want. This is once again a similar plot. You can see that we can also do exponential calculations with NumPy arrays. We can create plots similarly, and this also covers something called I forgot what this is exactly called. I think this is math tech. This is like LaTeX. If you have learned LaTeX, this should be almost identical for our purposes. It's just slightly different for Python. Let's run this and see what happens. You can see that you can use this to generate mathematical expressions, new labels, and new key, like this. Okay, the cube and 1/2 in the power. All of this can be generated with this. Yeah, this is the blue one. Well, log x. You can see that the scale is a bit messed up. So we can just comment out this line, and Matplotlib will automatically adjust to show us the other 3 lines more properly. Anyway, I won't spend any more time on this. We are already short on time. If you have any questions, please post them to the Slack, and I'll try to answer.
We have a quick question here, Aparajita,
Yes.
about in which what did you import here? Which module are you working on? Is the question.
It's these 2 modules, these 2.
NumPy and Matplotlib. Okay.
Yes.
And then another quick question: what does the R before the $ mean?
All right, good question. That's something called a raw string. Okay. So some of these things that you see here, they're not supposed to appear in the label, right? The dollar signs are not supposed to appear in the label. So if I remove this R, let's see what happens. It should work. Yeah, it did work. But it doesn't always work. Like if I say alpha, right? It will create the Greek letter alpha, right? But you can see that there's a backslash, and the backslash is basically a sign for an escape sequence encoding. So if I remove the R here, you can see that it generates an error message. So you should always put R in front of your mathstat expressions. Okay, so that's what the R is for. It just tells Python to ignore the backslashes, to not treat them like escape sequences. It's something called a raw string. Okay, I think we're good. Anything else? I will stop sharing my screen. And I think next up we have Cheryl. Correct?
Yes, thank you so much for finishing up Notebook 2 of Aparajito. And we are ready for our first astrophysics background with Geronimo. Hero.
Great, thank you so much. I will start sharing. My computer is a bit slow. Sometimes it glitches a little bit when I start screen sharing, but be patient. I will make it. Okay, so I'm trying to share now. Can you hear me properly? Is the sound okay?
Sounds good.
Okay. Okay, hopefully you can see my screen now. Let's see. Okay, maybe it's working now. Let's see. Let me know when you can see my screen. I think it should be there.
Yes, I can see your screen. It's in presentation mode.
Okay, perfect. So we're gonna follow a little bit this really cool presentation that I understand was developed a couple of years ago by Madeline. I really like the content of this presentation, and it is supposed to give us a little bit of context about the quantities, the observations that we can do about stars, and how like they can give us a broader understanding about that main object of study of astronomy. So let's see how it goes. Okay, let's see if this allows me to pass to the next one. Okay. So how do we describe stars? This is a really important question that astronomers have had to work constantly into understanding. So maybe try dropping some ideas in the chat if you want about what can we measure about a star to understand it better, to know something about it. Like what is something you would like to know from a star? If you could ask a star a question, or you could have a star in the lab, which is sadly impossible for humans. What would you try to measure from it? Try to put some ideas in the chat. I see there's some already coming in. Light intensity, color, luminosity, size, diameter, age. There's a lot of things that you're mentioning that are crucial for astronomers to try to understand more about them. And there's some more specific ones. Yeah, some people are saying here speed of recession, gravity. That is a very, very specific one that is very important for specific studies that we can do on stars. So let's talk briefly about some of them. We can measure how hot it is. We can measure how far it is, how big it is, how bright it is, what color it is. So these are some of the more qualitative ideas that we can understand from a star, but we need to quantify this. So we can say we can measure how hot it is through the temperature that it has, and we measure temperature usually in the units of Kelvin. So whenever you see the report of a temperature in a scientific paper, yesterday we were like trying to read a little bit through the structure of a scientific paper, understand how to read the information that astronomers find like about their findings. We will see temperature usually represented in units of Kelvin. We can measure distance, which is the idea of how far they are. And usually very popular in astronomy is the unit of parsecs. In our day-to-day lives, we are used, if you use the SI system, it will be meters or kilometers or stuff like that, or also miles, yards, it depends on the convention that you're more used to. But when we're talking about the astronomical huge distances that separate us from other stars, we usually need longer measurements or units of measurement that are much bigger than our day-to-day life units. So parsecs is one of them. You might have heard of light years, but they are not that common to be used on the academic world. In astronomy, for example, it's more common that you will see parsecs, especially for distances within our own galaxy. The separation between stars is usually measured in tens of parsecs usually. We can measure their size, how big they are, and the direct measurement of this would be their radius. And radii are usually measured in meters, or in solar radii also is another reference. So it's like comparing, in many cases you will see that we go back to comparing other stars to our own star, which is the sun. We can also measure how big they are, not only through their size, their physical size, but also how much mass they have, how massive they are. This can also be measured in solar masses, but also in kilograms you will see sometimes. But it is much more common to, again, go back and measure them, comparing them to how much larger or smaller are they compared with our own sun. And how bright do they look? So a star can be estimated its brightness with a quantity that astronomers have decided to call magnitude. You will see it as a capital or lowercase m, so uppercase or lowercase m. And the units are usually called units of magnitudes. It is a very direct name. So yeah, as a comment here, this is one of those units that is like a very arbitrary unit, because it does not come from relating other dimension quantities. Yeah, like quantities with a specific dimension. Instead, this is, we will see later, is a different scale. So we decide to arbitrarily name it magnitudes. It's similar as the case of radians that we use for angles. And we can also relate how bright they look with also how much energy they might be giving off, like how much, like internally, intrinsically, how much actual energy is coming out from a star. And this is what we call luminosity, and it's usually represented with the letter uppercase L. And it's usually also compared to our sun through solar luminosities, but also with the unit of watts, which is a unit, that's the unit that is a standard for physics. You know, in physics, when they try to measure power, so it's like how much energy is being emitted by per unit time, or like each second, how much energy is being is emanating from a source, like a star or a light bulb. It will be common to see this unit of watts. And what color it is, there is a very specific quantity that astronomers use that is called the color. And this is very ambiguous to say like this, especially after defining all these very specific units of measurement coming from very clear physical quantities. Color sounds a bit more arbitrary, but we'll discuss it in a bit more detail later. So let's chat a little bit about the magnitude scale. There is something really cool that I heard Raja once say about the magnitude scale, is that there's like 3 ideas that you have to grasp, and it will take some time. Like I learned about magnitudes, say, a bit more than 10 years ago, I think, and it's still sometimes confusing my head because it is a like inverse scale. So that would be the first like idea that we have to grasp from the magnitude scale, is that it is inverse. So when we give a star smaller value, it means that it's a brighter star, and when give it a high value, it is a much fainter star. So just to give you a point of reference, our limit, usually the standard of the limit for our naked eyes for looking around us, is around 6 magnitudes. So we can see everything that has a magnitude usually below 6. So if you read a star chart and it says that some star that you are interested in has a magnitude of 6 or 7, it's likely that you will not be able to see it from where you're standing at. Instead, if you go and look for a star that has a magnitude of 0, you can expect it to be a very bright star. So this is kind of the idea. The first idea is that smaller numbers or more negative numbers are brighter, and the higher numbers are fainter. That is the first idea that we have to grasp. We also have to grasp that it's a logarithmic scale. So you cannot expect, for example, a magnitude, like if you have a magnitude value and it's half of another magnitude value, it's not going to be half as bright, or like it's not going to be double as bright, you know. It is on a logarithmic scale, and this is sometimes a scary word, but it's nothing to be scared at. It is very natural, actually, to our senses to have logarithmic quantities. Our hearing is actually worked also in a more logical way if it's a logarithmic scale. The way we feel pressure on our skin also is logarithmic, because evolution has made us this way. It's actually very interesting that our eyes have been calibrated, and our ears, to make it more relevant to differentiate between 1 or 2 sources of possible threat than 15 or 16. You know, when you go to higher numbers, it's not that relevant, that same difference of 1, as it is for lower values, you know. So this is the case also for brightness. So it is a logarithmic scale. And then you can also say that it is a scaled scale, which is kind of a weird thing to say, but it is scaled. So it is not straightforward like logarithmic scale. There is like some factor of conversion, and this factor of conversion is historical, that a difference in 5 magnitudes. So if you jump, for example, from 1 to 6 magnitudes, so if you say one object is magnitude 1, then you go to an object that is magnitude 6, that is a difference of 5 magnitudes. The difference in brightness is 100 times. So it is physically 100 times more brighter, like you're receiving 100 times more energy from that source. That is value 1 in magnitude, than from one that is 6 in magnitude. So that is a central idea that we should keep in mind. And this is historical. The scale was defined many, many years ago. It is related to the early Greek astronomers that wanted to make like a scale of 6 ranks to classify stars, so from 1 to 6. And since they also invented the Olympic Games, they were like, okay, who is the best one? It's number one. So that is why that is brighter than number 2, number 3, and number 6. But then it became harder to keep track of which stars are brighter or fainter. Yes, Janika.
Quick question, I think related to brightness. Is there a formula for brightness, apparent magnitude or absolute magnitude, since they're both log scales?
Yes, for connecting brightness and because brightness is something that we measure as apparent, is something that this is something that I haven't introduced yet, but when we say apparent, it's just as you see it in the night sky, for example, if we're talking about stars. So there should be a way to relate this arbitrary value that we're giving it, that was first given by eye, but then it was calibrated as this scale that you say, okay, a difference of 5 means a difference of like a ratio of 100 times more bright. This should be like a hint to a relationship, and this is due to an astronomer which his last name was Pogson. You can find it as Pogson's law, and there is Pogson's law, which is like the relationship between the magnitude value that you should give to a star depending on how bright it looks. So you can find it as Pogson's law, and that is like the mathematical formula. I think we don't have it here in these slides, but it's easy to find, and it's fairly simple, just relating through a factor of 2.5, something like that. You relate the ratio of brightnesses of two stars with their difference in magnitude. So that is the cool part where the logarithm kicks in. It's like a ratio in the actual brightness you're measuring turns into a difference between, so just like an almost subtraction of numbers between their two magnitudes. So yeah, you can look it up as Pogson's law. It is really, really nice. So as we were speaking, we say that this is apparent magnitude, and this is what we usually denote as lowercase m. And apparent means, okay, it's just like you see it in the night sky. And this is very, very important because something looks brighter than some other source. So if you're looking at a star, it looks very bright, and then you look in another direction in the night sky, and you find another star that is less bright. Do you think it actually means the brighter one is actually emitting more powerfully? You know, like it has more power to emit? Not necessarily, right? It could be that they have the same power to emit light, but one of them is far. So then, yeah, a great analogy for this is like comparing just a small light bulb that you have maybe in your room to the headlights of an airplane or something like that, like a big light. So just because you see the airplane from your room, and you compare the brightness of your own light bulb, and it's brighter than the headlight from the airplane, it doesn't mean that your light bulb is more powerful than an airplane headlight. You know, it means that maybe that other source is very, very far. So then we need to scale things in a more fair way. You know, we have to do it in an absolute way, and that's when absolute magnitude kicks in. Then we define distance, because we're talking about stars. We need to use a star-like distance, which is 10 parsecs. And we say, okay, let's imagine we could stand at the same distance from every star. Like we could take every star and push it or pull it to a very specific distance of 10 parsecs and measure its apparent magnitude then. So then we call that the absolute magnitude. And that's a more fair way to compare how powerful different stars are. So that is a very interesting difference that we should do. And this we will denote with the letter capital M. We'll do uppercase M for absolute, lowercase m for apparent, and you will see it a lot around. Okay, so then comes something more specific, which is, okay, first, like historically, humans measured magnitudes by eye. It was like just, okay, this looks brighter than this, so I would say this one is number 1 and this other one is number 2, okay? But then when astrophysics became a thing, you know, when people joined forces to say, okay, let's make more quantitative results from what we're observing in the night sky, we found out about some very, very useful concept that electromagnetism brought for us, which is the wavelength of light. And wavelength is an indication of the color of the light that we're seeing. So here in this graph, we have a range going, spanning a bit more than the light that our eyes can see. So our eyes are thought to be sensitive from somewhere between the start of this graph, around 3,000 to 3,500 angstrom, maybe being very, very generous, all the way to 7,000, also being a bit generous. And that is the going from the left to the bluer side. Yeah, the bluer side is to the left of us, and to the right is redder. So this is the visible spectrum. And we have a little bit more in this graph showing a little bit of the ultraviolet, which is denoted here on the side that says U, and a little bit on the infrared, which shows here with the I. These letters are not just random. This is a system that we call a photometric system that was decided like this because notice what I was mentioning. The idea is to stop using just our eyes to say, okay, this kind of looks more bright or this kind of looks less bright. We needed to start using detectors, devices that can catch the light and actually measure how intense is the light that we're seeing. And these detectors are not equally as sensitive in different colors, in different wavelengths. So we need to standardize the way that our detectors are going to catch the light on each specific color. So the way that you do that is called a photometric system. And this is called usually Johnson's Cousins photometric system, UVRI. And it goes from the more blue violet side on the U to the more red or infrared side on the R and I. And we can define color now with this, that I said it was going to be a bit ambiguous before. We can define color now as the difference that you measure in two of these different bands. So if you think that you're observing a more like a bluer object, this bluer object will correspond to a smaller value in this color. So in the difference of the magnitude that you measure with two of these filters. We usually call each of these little color windows, we call them filters. So it's very common that astronomers will report they observe a star in several of these filters, and then they report a color value, which is the difference between the magnitude you observe, for example, in the V band, which is here in the middle, which is more green, yellowish, and the I band, for example. So you can define the color in the V band minus I band, right? So you usually go put like the bluer one and then subtract from it the redder one, and you define that as a color measurement. And if you get a smaller value, you can then infer that your object, the source that you're observing, is bluer. If you get a bigger value, then it's a redder object. It's a redder star, for example. But this is not the only way we can define it, and it is not perfect, definitely. On top here, we have the photometric system that was used for a very, very cool survey called the Sloan Digital Sky Survey. And they had to define the way that in each color band, in each filter, they were going to catch light for every star and galaxy, because they really observed a ton of galaxies, and it is a very useful survey for astronomers even nowadays. And then they had to define this very, very clearly for everyone to know, okay, how true is the measurement of magnitude that I'm getting from using the U band or from using the R band from the Sloan Digital Sky Survey? Because when you compare the coverage that it has, you see that on top, what is the area that these curves are looking at. You can see that when you compare with a very real spectra, when we do plots like this for how bright are stars in all of the wavelengths, we call them spectra, or spectrum is the singular, spectra is the plural. And you see that we cannot cover with most instruments, with most telescopes, we cannot cover all of their spectra, because their spectra are so big. They cover a ton of wavelengths. So we can only cover part of them. So we need to really, really know how our instrument is capturing that light, and then understanding the way we're measuring the magnitudes, all the astronomers can compare the results and they can know what they're talking about. So that is very, very important. This is why we put such an emphasis into understanding photometric filters. So this is also very cool. Also, maybe another telescope that you've heard of, Hubble Space Telescope, right here. is also very relevant for understanding its filters, and there is some very popular filters that you may use also in some of the activities here with the notebooks, like this F476W, F814W. These have less charming names, I guess, but you can see that it has a very, very good coverage going from 2000 angstrom, which is one of these units that we can use to measure wavelength. So this is a measurement of length. And it goes from very, very short wavelengths. So this is pretty much ultraviolet across the visible around here, 5,000, 6,000. You can usually say that this is definitely visible, or optical. You will see it a lot too. And then when you go past 7,000 or 8,000, you can see it has also a lot of coverage in the infrared. Which this coverage outside of the visible, mainly on the ultraviolet or the infrared, it's very useful for a space telescope, because our atmosphere will usually not be transparent for those wavelengths. So we could not see many things that Hubble made possible and other space telescopes because of our atmosphere. So it's nice to have, this is why it's nice to have space telescopes. So yeah, this is a bit of that. And then we can jump into something interesting, is that now we know how to measure colors properly and characterize our stars as bluer or redder, and understand that there is a connection between, there's a connection between our magnitudes, right? And how intrinsically bright our stars are. We can construct a diagram like this. This is called the HR diagram. It's short for Hertzsprung-Russell, which were two American astronomers. And this is like a chart that we can use. It's like a cheat sheet that we can use to know stuff about stars that we are observing. So if you take every star in the night sky and you put it in a diagram like this, you will be plotting in the x-axis. You will have something related to its temperature. And notice how this is also, astronomers really love inverse scales. So this is growing temperature towards the left. So the stars that are more towards the left are much hotter than the stars that are more towards the right. And then on the vertical axis, on the y-axis, we have the luminosity in solar units. So this is solar luminosities. So if you go to 1 here, you will be in the range of luminosities of things that are similar to our sun. So you can see the sun here. And you can also note how if you go diagonal to the right, going kind of towards the upper regions of the upper right regions of the diagram, you can also see how radius grows. So that's very interesting. So larger stars will be found more towards the right top corner of this plot, and the smaller ones are going to be focused on the left bottom corner. So this is very useful, because when we take a snapshot of the sky, like we try to measure all of these values for all the stars we know, and we try to plot this, we can have a lot of information about what stage these stars are in their evolution. Are they supergiants? Are they giants? Are they in what we call the main sequence, which is like all their adult life? It's like the youth and the adult life of a star after it's born. Or is it very weird and maybe last stages? These are like elderly stars that we call white dwarfs. So this is very interesting to trace the evolution of stars. But also, if we know that, for example, we're observing stars that have the exact same age, and this happens in, for example, in clusters, in star clusters, we can also understand what is the population, like what are the main features of the population that we're observing. So it is a very useful diagram that if you're going to continue to explore the beautiful topics of astrophysics, you're going to stumble upon again and again, and it is a very, very useful tool. So yeah, this is one small, simplified version of an HR diagram, which displays a little bit some of the phases of the evolution of a star. We mainly, as I mentioned, speak about the main sequence here, which is like the main part of the life of a star. Usually happens during the main sequence, which is described mainly by the core of the star fusing hydrogen, which we can talk about as the fuel of stars. But then it will there will be many changes inside of the star that will make it jump and go into this other phase called the red giant branch. It will then go to the horizontal branch, asymptotic giant branch. Many things can happen, and it is all determined by the initial mass of our star. So if stars are very massive, this process will be very quick. If stars are less massive, then this will be very slow, and maybe some of these stages will not happen at all. So yeah, stellar evolution is a very complicated process, but it is very beautiful. And these diagrams are one of the tools that we have to observe it. We can go quickly to check this out in a short animation here. If you're seeing it, maybe you can see how this little star that has the mass of our sun is starting to the right of the diagram in a very cold and not so bright spot. And you can see it does like a little trip into the main sequence, and that's when we say it is born as a star. It starts its proper star life, and then it jumps out of the main sequence after some time, and it starts its journey through the red giant branch and these other more advanced stages, until if the conditions are right, for example, for our sun, it will happen. It will go back into becoming a white dwarf, and that's where it's going to end its life after many, many years. It is a very long process that will take even longer than the universe has been existing for. So this is again a very, very interesting topic. Let's go back here to the presentation. We're about to finish this this introduction. I try to be very brief, but yeah. So one little detail that we have to take into account is that I mentioned HR diagrams have on the x-axis temperature, and on the y-axis you have luminosity. And these are quantities that are kind of hard to measure. You know, it's you cannot jump into a spaceship with a thermometer and go and measure if a star has fever. You know, you cannot measure the temperature of a star with a thermometer. You have to use techniques that come from this light, that come from this the measurements that we do with this photometric system that we saw, that do not capture completely the spectrum of the star. We need to use small snippets of the spectra to infer things from the star. So usually, since this process of converting the color measurement into temperature can be a bit delicate, can be a bit of a source of debate between astronomers. There's different methods, different formulae that you can use. It's more useful sometimes and more direct to measure color, understand which photometric system you're using, and plot on the x-axis the color, which will be kind of related to temperature. So to the left, it's a smaller color value, to the right is a higher color value. So you can see, as we said earlier, to the right is redder stars, to the left is bluer stars. And this is very interesting. In astronomy, when we use the word bluer, it is a synonym usually of hotter. So the hotter stars are going to be more to the left. The colder, like cooler stars, are going to be to the right, in the redder side of the diagram. So we plot color on the x-axis. And in the y-axis, we can plot the absolute magnitude. So you see that we have M, capital M right here, measured in magnitudes. So if we have a way of measuring how bright we see the star in the night sky, which would be its apparent magnitude, with its distance, there is a way that we can figure out how bright it actually is, how bright, how much energy it is emitting, which is related to its luminosity, but also to its absolute magnitude. So when we plot absolute magnitude here on the y-axis against color in the x-axis, we call this a color magnitude diagram. It's very direct naming. And this is also very useful. And it is pretty much equivalent on the distribution that you see to what you would observe usually in an HR diagram, but it is also something you will stumble upon surely if you keep following the track of stellar astronomy, stellar astrophysics. And this is very cool because you can see there is a color division in this diagram, and astronomers very quickly define some groupings that you could do depending on the color value that they measured, and they gave these categories these names, which are B, A, F, G, K, M. We can be missing maybe O in this specific diagram because O is a very, very massive star, very exclusive range for stars with incredibly high masses that have very short lives. But yeah, so this is very, very cool. So we can leave with some questions that we can maybe try to answer together. So one of these is maybe for you to reflect on. What is the magnitude of a star? I can say it fairly quickly. So it is an arbitrary unit of brightness, of apparent brightness, that humans gave to objects they saw in the sky. What do you think is brighter? Now I need your help in the chat. What do you think is brighter, a 21 magnitude star or a 10 magnitude star? I think it should not be after what we said. So a 10 magnitude star, as some of you guys are now mentioning in the chat, is definitely brighter. So this is one of those exercises where you have to remember. And 10 is already very high. It's beyond the limits of our eyesight. We cannot see a magnitude 10 source. So very good, everyone answering magnitude 10. What does a star change as it ages? Okay, this is more a stellar astrophysics question that we can reflect on maybe later. We can discuss. If you want, also, I will be available in the Slack channel for discussing some of these topics if you have further questions, so we can move forward with the notebooks today. The color, as we mentioned, it is this definition that is kind of vague at the start, but then when you define properly where are you measuring these magnitudes, you can find a definition of color as the difference of brightness in two different wavelengths. So this is also very interesting. And how do we measure the temperature of a star? This is a very tricky question, and we can also leave it for further discussion on Slack, because I don't want to overstep here on the time of the other activities. So yeah, I think we're done here for now.
Excellent. Thank you, Geronimo. Yes, we do have some questions that were posted in the chat, and so as Hero requested and suggested, please post those questions over in the Slack channel so that you can get some good detailed responses to your questions. All right, thank you so much, Hero. And now we are ready for our next section. This is going to be Notebook 3 with Madeline.
Thanks so much. I think Hero did that much better than I have ever delivered it, even though I made those slides. Thank you so much, Hero, for doing that.
Oh my God, of course. But you know, we're standing on the shoulders of giants, always.
And that's how science works. Now, do we have time to take a 3-minute break for our students?
Absolutely, we certainly can do that.
All right, let's meet back at 12 after the hour. So that's 3 minutes now.
Heidi, those are really amazing slides. I've used them so many times, and I just sent you a quick note and email about the yes, your designation on the CMD is fine, and I can hop on if you at any point just call on me. I can hop on and explain why the main sequence looks so strange in that diagram. It looks vertical, right? And you're used to the main sequence.
That's true.
Yeah, main sequence is normally diagonal in an HR diagram, but in our CMD, why is it vertical? There's a very simple explanation for that. What happens is the two filters we have, 475 and 814, are so long, the wavelengths are so long that they are completely on the Rayleigh side of the blackbody peak beyond a certain temperature. This is true for any pair of filters. If they're completely on the Rayleigh side of the blackbody peak, they're no longer sensitive to temperature because they're seeing the same slope.
Yeah, of course.
As you increase the temperature. So same slope means same color. And that's basically what happens for this. If our shorter wavelengths were shorter than 475, then we would see a tilt. And then even that would ultimately become vertical at high enough temperature.
Wow, that is so cool. You're clarifying so much things for me right now, because I did like work on a color magnet diagram for an open cluster some months ago. And there was always this idea of like, why are we losing a little bit that tail? You know, like it really loses the inclination. It really makes sense now.
Well, essentially, it's such a nonlinear mapping. When you have color on the x-axis, the mapping of color to temperature is such a nonlinear thing. And nonlinear to the point when it becomes flat, there's no sensitivity anymore. No longer dependent on temperature. Essentially, that's what.
So there's a question. I think we should try to answer that over audio and video, which is, how is R set defined essentially? Jamin asks, I know that a parsec stems from the stellar parallax method, but how do astronomers come to the value of 1 parsec from 1 arcsecond? So let me see if I can try and answer that. So what is parallax, right? What is parallax? Let's try to understand what is parallax. I want every one of you to hold out your hand like this, hold out your thumb like this in front of your face, okay? Close your left eye, look at your thumb, try to line it up with something in your room, anything, line it up perfectly. Keep your left eye closed. Now, open your left eye and close your right eye without moving your thumb, all right? Without moving your hand. We'll see that your thumb is moved, all right? So that is parallax, okay? If you're looking at something from a distance, and if you move laterally with respect to that object, to your line of sight, that object will appear to move slightly, okay? Now, you can measure this movement using angles, all right? We will learn about astronomical coordinates at some point, or the very basics of RA and DEC in there. But you can essentially think of the whole sky as a sphere. You can divide that whole 360 degrees into smaller divisions. And you can measure this displacement, this apparent displacement of your thumb, okay? Or in case of astronomy, a star, using angles, okay? So, okay, Raja, you have raised your hand. Yes, please go ahead.
Quickly, I just wanted to say that in your analogy, which is a beautiful analogy, this gets used very effectively. Your nose, you can think of, or the bridge of your nose is the location of the sun, and each of your 2 eyes is the position of the Earth 6 months apart.
Yes, that's excellent. That's really, really good. Thank you so much. Yes, so that's the parallax method in astronomy, all right? You measure the exact position of a star, a faraway star, and then you measure it once again accurately 6 months apart. 6 months apart means that the Earth will be on the exact opposite side of its orbit, right, than it was 6 months before, right, on 2 opposite sides of the sun. And these 2 positions of the Earth will be separated by twice the Earth's sun distance, all right? And then you can do a little bit of trigonometry and figure out, since you know the distance from the Earth to the sun, and since you know the angle of displacement, okay, the apparent displacement of the star, you can figure out the distance to the star. Now, if that displacement, that apparent displacement, is 1 arcsecond, okay, then that distance to that star from the sun is the average position of the 2 positions of the Earth, right? The distance to the star from the sun is 1 parallax second, or 1 parsec, okay? A parsec is a measure of distance, a measure of astronomical distance, not speed or time or whatever it was in the first Star Wars movie. It is a measure of distance, okay? So that's how 1 arcsecond, 1 apparent displacement of 1 arcsecond is translated to a distance of 1 parsec.
Aparajita, I just wanted to add one more thing, which is the formal definition of parsec is if a star is a parsec away, the angle change between 6 months is actually 2 arcseconds. So it's 1 arcsecond on either side of the sun.
Oh, right. Oh, no, sorry. That's a very critical mistake. Yes.
Could you think of a right angle triangle, basically with a vertical line connecting the star to the sun, and then the Earth off to one side? That angle at the top is 1 arcsecond. So it's the half angle between the positions of the Earth 6 months apart. But there are many diagrams about this out there about parsec.
Thank you, Raja. Also, I want to quickly point out that we have been talking about color. When you talk about color in astronomy, Harold pointed out that it is a different quantity, but I want to re-emphasize that because it's going to be very important going forward. Color is a completely different term in astronomy. Color doesn't mean color as we understand it in daily life. Color is basically the difference between two magnitudes measured in two different filters using photometry. We'll look more into it, we'll work with it, we'll measure the color, create our own color magnitude diagram. But whenever you hear the term color from here on, just know that it is an astronomical term. It does not mean, red, green, yellow. That's not what color is in astronomy. Yeah, that's it. I think the break is very much over. I'll pass it on to Maddie.
Wonderful orientations, everyone, for what we're going to be doing next. Can everyone hear me? Looking good, okay.
Yes.
All right, so we're on to notebook 3. So everyone pull up this notebook here. I'm going to try to keep the chat open for your questions and suggestions, but if I miss anything, other mentors, please elevate what folks are saying in the chat. All right, so as we just heard from Parito, we are going to be making a CMD, a color magnitude diagram, and this is actually from that splash survey that they talked about in that first paper. This is real data from Andromeda. So we're going to start, as we always do, by importing NumPy and importing Matplotlib. Once we've clicked through that, remember Shift and Enter is what executes a cell. And so this next cell is just a personal preference. Here is where you can set the settings of things like your font or your font size to be the same across all of your plots. You can do this individually for a plot, but it gets kind of annoying to have to do it for every single plot. And so this is just kind of universally setting it to be a serif font and a font size of 14. All right, so this next cell, we're not changing anything, but we are going to explore what it defines. So if you recall, this is a function. It means that running this cell isn't going to change anything, but every time we call this function initialize plot after this, it's going to execute what is inside this function here. And so what this function is doing is it's creating a figure, kind of like the axes on a plot, but they're empty. And so we'll have to put in the data afterwards. So it's making a figure, plt.figure. It's setting our figure size to be 8 units by 8 units. You can change this to whatever size is your personal preference. We are setting our limits on our x-axis between -1 and 9. Limits on our y-axis 24 and 18.
I can. Yes, there's one sample that's an outlier. 1CD9, that's an outlier.
Let's go ahead and mute, I think, unless we're answering questions in the chat. All right, so to quickly finish this function, we're labeling our axes. This is incredibly, incredibly important in science. Always label your axes, even if you're just making a very, very simple plot so that everyone knows what it is that you're plotting. So we're going to be plotting here F47W and F814W. Where did we just hear those names? Those were the names of those filters, those bands that let the light through. And so what we're doing here is we're comparing the magnitude or the flux in each of these two. And when we take the difference of two magnitudes in two different wavelength bands, what we get is a color. So we can tell already this plot is going to give us color on our x-axis and then flux or magnitude on our y-axis. And so that's what a color magnitude diagram is. Color on one, magnitude on the other. So next, this is also a function you're not going to need to modify. This is writing a catalog. And the reason we're doing this is because we want to save our data. We don't just want to make these beautiful plots and then not analyze them or do anything with it. We're going to save the cuts we're going to make in this population of stars as we label them with different populations. And we're going to write out a catalog. And this function, you'll notice, is called write catalog, but doesn't have empty. It doesn't have nothing between these parentheses here. This time we have arguments, as we call them, in this function. We have an argument you can input called catalog name, an argument you can input called parameters, and an argument you can input called param name string. So the name of your parameters that are going to be the headers of each of these columns that we're going to write in. This function here called open, you'll notice it's in green, which means that it's a default function. You can't just call something like a variable open because it always means this function. So that's in green automatically. And so open opens a file, and we can write into this file whatever we want to if we have this little command W here. W means write. There's a couple things I can put in here. I can put an A in here, A plus, and that will append if I re-add things to this file, it'll just add a new line to the end, new line to the end, new line to the end. I can do R, which is just read it, don't actually write anything into it. But we're going to use W because we want it to write itself completely every time. And this means it's going to overwrite itself, so be careful. If you run this again, you will overwrite what you did. So we're going to make sure we have the right data we're putting into each of these files as we write them. So it's going to write out our first row with the param name strings that tells us that it's our first column. That's giving names to these columns, so it's easy to tell in the future what we wrote into this file. And then we're just looping. Remember our for loops from earlier? We're looping over the number of stars and over the number of parameters so that we can make a list of these variables that are going to be in each column. And then very important, we write them out by putting the write command. So catalog.write means write me this line, write me this line. This command here, or say this slash and n, always a backslash, means make a new line. Because if you don't do that, which I've forgotten many times, what you'll end up with is not many rows of data. What you'll end up with is all the data squished back to front with no spaces or lines or spaces, no spaces or gaps in between it. So always create a new line. And then we close our file. If we don't close the file we've written in, you will run into trouble. You can accidentally overwrite things. Sometimes it won't even write at all unless you close it. So always close that file. So what does that even look like? We'll give ourselves a quick cheat ahead. We're going to be using this. This is not something you're writing. This is data you're given in your data folder. But this is what it will actually look like. Something like this, where we have columns and rows of data. And this is, for example, your param name, as they called it, which is the title of your column. It will tell us that everything in this column is RA, which is a value of a unit of a coordinate in astronomy. So those are our positions. All right. So I would make sure I ran these. Let's restart everything just to make sure we're running everything cleanly. Importing NumPy, setting my matplotlib desired parameters, creating this function, creating this function. All right, so we've created the functions we needed. We've imported everything. Time to do some science. So let's take a look back at that data set here. You don't have to open this yourself. I'm just going to show you what it looks like inside here so we understand what we're importing. So we see here that there's 1, 2, 3, 4, 5, 6, 7, 8, 9 columns, and they have these different headers that tell us what they are. So what we're doing in this next cell is we're loading in the text file. So np.loadText is going to read in this text file that lives at this location. Now this is where it lives. So if I were to follow that through all of my Python notebooks that I downloaded, there should be a folder called data, and inside you would find this file. And this ... just says where I currently am sitting in my files. I want to go one file higher and then back down to another one called data. And then unpack is just unpacking our columns of data that we saw. And so in here already should be the names of each of these columns as we see them in this data file. And then we're going to go ahead and we're going to make the calculation of color already, which we know is the difference between the magnitudes in these two bands, F475, F814. Let's execute it. All right. So now what happens if we plot that color magnitude diagram? We know that initialized plot is going to create sort of the axes that we need, but we still have to populate them. So how do we populate those axes? Well, we plot something. In this case, let's make a scatter plot because we want to know where our stars sit in color and also in magnitude. So in our x-axis, remember it's color, and then on the y-axis, it's magnitude. And then what we're setting here with the command C, or the variable C, is color. So color equals gray, just a choice we'll use to highlight our later populations. S3, this means size is of 3. I can change this variable to mess around with it, just see the effects. And then edge color is equals to none. That's just a setting you can set on your scatter plot to make your points even fancier. All right, I'm gonna zoom out a little bit so we can see this all in one page. All right, so we have here exactly what our initialized plot function promised. We have an x-axis that runs from -1 to 9. We have this label here that tells us this is our color axis. We have magnitude and range we expect, and then the magnitude label here. And these are our stars. This is how the population of Andromeda star, this is actually HST, I realize now. HST is the Hubble Space Telescope data for Andromeda. And these are all the stars, where they lie in their color and their magnitude. Now, it's not as nice looking as the one that we saw at the very end of the talk we just listened to. And that's for some nuanced reasons regarding how bright these stars are and the limits of the telescope that Raja explained a little bit over the break. But we can still kind of see some distinct populations. If you were asked just blindly, knowing nothing about astronomy, to divide these up, how would you divide them up? I think I'd take a look here and be like, okay, this lump is different for some reason. This kind of looks like a lump over here too. Maybe this is like part of the same lump. Maybe it's a separate clump here. And indeed, this is the kind of data that astronomers first got when they were making the Hertzsprung-Russell diagram and other similar color magnitude diagrams. And they said, is this just like a coincidence that all these stars are clumped up in different areas? Or is this in fact scientifically significant that they're clumped up? And indeed, it is scientifically significant that they're clumped up. These are different populations of stars. And when I talk about a population of a star, I'm talking about sort of different types or different ages of stars that are all alike. And so we saw that main sequence where most stars hang out for the majority of their lifetime. So let's go ahead and we're actually going to plot where that main sequence is. Let's scroll down. And so you can read a little more here about the types of populations that we're going to plot. So what we're going to do, make sure I don't scroll too far so you don't see anything you're not supposed to yet. What we're going to do is this cell here, you're going to copy numerous times and you're going to modify things in order to plot these different populations. So this one's already filled for the main sequence. So we're just going to walk through what it does. This MS stands for main sequence. And here it has this interesting syntax of, some parentheses, an and sign, and some more parentheses. What this is a mask. It's called a mask because it, like a mask over your face, masks data in a certain area. And we're telling it here what area we want it to mask. And in this case, we want all stars that have a color less than 1.75 and all stars that have a magnitude greater than 23. So where do we predict we're going to be masking on here? If we have a color greater than, say, 1.75 about here, and a magnitude greater than 23. That's there. So I want everything less than 1.75 and everything greater than 23. So my prediction is we're going to be masking this area here. Let's see what happens. We're initializing our plot. We're plotting our color and our magnitude. We're going to replot those original, all the stars, just so we can see what we're covering. And then on top of it, and this is important that it's second, because we'll always plot on top what is later in your list of things that you're plotting. We're going to plot another scatter plot, and we're going to say, give me all the colors that fit this mask, and give me all the magnitudes that fit that mask. So these requirements here in our X and Y data. And then we're going to change that color so we can see that it's in fact distinct. Changing it to blue now for the main sequence. And what we're doing here with this command plt.text is we're going to write a little label. We're going to color it blue. We're going to put it at this X position and this Y position. And this is setting our font size. All right. Then we'll get into this later, but you are going to write it to that catalog using the write catalog command. But before we dig into that, let's just see what we plot. Okay, was our prediction correct? Looks like it. So this population here is the main sequence. And indeed, we covered in blue every point that was less than 1.75 in color and greater than 23 in magnitude using that mask. And so now, using that data that we've cut out here, we are able to write that data to a catalog, and we're going to call that catalog main sequence or ms catalog.text. You can technically name it whatever the heck you want, but this is a nice informative title, so I'm going to leave it. And you remember we have to write our columns and then the column names here as our other arguments and inputs to this function. But notice something specific. I'm not just writing out all of the data of all the stars. I'm writing out just the data that we masked, just the data that we cut out. So what's going to be in this file is going to be all of the main sequence stars that met this criteria here. All right, so we've now saved that, which means we can go back to those data, we can plot them again, we can do science on them, we'll actually count them up later in this. But now is where we get to the fun part. Remember we said there's some interesting looking clumps here. And indeed, they do correspond to different populations of stars. So the two different populations of stars that we are going to plot are going to be the AGB and the RGB. So RGB is those red giant branch stars. Those are giant stars that are heading towards the end of their lifetime. They are expanding, turning redder in color, getting larger, and also being much cooler. So I'm going to copy this, you copy this, and put it into a new cell. Remember, you can create a new cell with this plus button up here. And I've just gone ahead and I've already copied it into here. All right. So what are we going to do if we want to capture just these stars here? Well, Raja, or I guess Claire, who created this, suggested that we use a parabola. So a mask doesn't just have to be a big square of less than this amount or bigger than this amount. It can actually be a shape. You can say all points that fit within this circle or all points that fit within this, triangle or something like that, as long as you can define those edges by some sort of function. So what we're going to use is a parabola. And so we're saying we want all the colors that are greater than 1.75, so everything that's to the right of this here, and some function here. We want the stars to be greater than this. Now, admittedly, I haven't thought much about parabolas since high school, and maybe you've not encountered a parabola yet. And so I pulled up this awesome online graphing calculator tool that I use all the time as a professional scientist called Desmos. And I put in this function here, a parabola. And so what happens when we change each of these parameters? You're asked in this notebook to guess what some good numbers will be. And I just want us to understand how what we're changing changes things first. So see this A here. The A is out in front of our parabola. What changes if we change that number? Make it bigger. Okay, our parabola gets narrower. We make it smaller, our parabola gets wider, and then eventually turns upside down. Okay, good to know. I'm going to set it back to 1. What about H? H is this value inside of our square. Okay, H scoots us. That's good to know. So I set H to 2. It's going to be scooted over to 2 here on our x-axis. All right, let's set the x to 0. So H controls how far we go sideways. K, what does K do? Okay, K controls how far we go up and down. All right, so if I set K to 2, it's going to be at 2 on the y-axis. All right, so now we have a good handle on how we can change this A, H, and K to change things. So let's make some guesses. We want to capture, oops, no revealing things. That's also not what we're plotting anyways. We want to capture this population here. So where's a good place to like start putting our parabola edge? Or sorry, we want to scoot right and left. So scooting right and left is that value H. I'm gonna guess that like maybe 2 is a good place to put that. I'm gonna set our H value to 2. All right, I'm not gonna mess with A yet because we'll see what we get and then we'll mess around with A. And then K. Do I need to go up or down at all? K controls how up and down we go. I mean, maybe. Let's put it at 23 again, just to see what happens. We want our K value that controls how up and down we go to be 23. Okay. So we've put some guesses in here, educated guesses. And we're now going to look at this function that we've done. We've copied this directly from above, so everything's the same. But should everything be the same? What do we need to change here? What about, let's search for every place that it says MS. Yeah, we're no longer plotting the main sequence. So we have to change this. Now look at what our mask is called. Our mask is called RGB for our red giant branch. So I'm going to change this to RGB, saying, please make the cuts where I want to see the RGB stars, RGB. I'm gonna call it RGB2 for this is plotting our title of our section, or sorry, this little text title here. I don't know. It says red in the name, so let's make this red. Where else do we have MS? Okay. Oh, this is important. Remember what I said about overwriting your data? We do not want to overwrite our data we just made above. We could always rerun it, but let's change the name of that so it's writing it to a distinct text file where we can save this. And I'm going to change each of these to be RGB as well. Remember, we want to make these cuts where our mask is telling us. And so if I had done this and kept it as MS, it would have put exactly the same population as these main sequence stars into our folder called RGB. And that's not what we want. We want the actual RGB data. All right, so we're going to execute this cell and see what happens. Okay, so I've made a mistake here. What do we think happened here? Look, it's just capturing the ones down there. Okay. A times minus H plus K. Let's return to this. Minus H plus K. Well, I'm going to guess based on the fact that it's wants the points that are greater than that. Let me try messing around with some variables. When you said H of 2, it seems
And
like it
Maddie,
is centered on
I've
2.
put some numbers in a direct message to you, Maddie.
Okay.
Sorry.
Thank you.
Sorry to interrupt.
No, that's good. All right. All right. So we have some good guess points already to start. I'm going to make some more educated guesses based off of what Raja has indeed sent us. So let's mess around with this value of K. Use Raja's suggestion here of 20. Ooh, okay. So we needed to scoot our parabola up, apparently, in order to get that. All right, but it looks like we're not capturing all of this clump of stars. Why is that? We need a wider parabola. Remember what made our parabola wider? Was changing this A value. So I'm gonna really, really lower this by like a factor of 10. Ooh, okay. Much wider swath of the population captured. Probably too much, because we can kind of see that there's an edge here, that these two here and here might be distinct populations. So I'm going to raise A a little bit.
And you want a K, Maddie, that's a little bit lower, not quite 20, but 20.5. Because that's the peak of the parabola. And you could actually yeah, there you go. That looks so beautiful.
Yeah. All right. And so these are values you can and should experiment with for yourself. In order to constrain these, you can revisit your graphing calculator to understand what things do, or you can just make educated guesses about what happens when I raise A, what happens when I lower A, okay, what happens when I raise H, what happens when I lower H. That's really what we do as scientists when we're experimenting with these values, is understanding how changing one parameter, as we call it, one of these values here, is going to affect our results, just to get a handle on it. Okay. I don't know about you guys, that looks like a pretty darn good red giant branch population here. We can scoot over, I don't know, it's super necessary, but we can scoot over our RGB label. Okay, awesome. Now, I'm going to leave it up to you guys to find the rest of this AGB, because I want to keep us moving along. But I'll point out that here we have our main sequence. Here we have our red giant branch. And then our asymptotic giant branch is this extremely, extremely, extremely brief period in stars' lives when they have gone from the red giant branch over and are about to decay and die. This is a brief period in their lives in which they will become more luminous, but stay very cool as well. And so think about what we did for our masks. Think about we want something to be greater than 1.75, and we have a pretty good boundary here. And we said we want everything less than that. So how would we get something that's more than that? My suggestion would be to flip that sign. All right. And the reason we're moving on is we actually want to do a little bit of analysis on this data. So here's where you can fill out your AGB, experiment with those choices, see if you can get it to plot different color here, maybe make a combined plot with all of these different ones labeled, so you can really see those different star populations distinctly. All right, so here is where it matters that we saved this data. That and that. So what I've done here is I commented out the AGB part of it, just so we can do this quickly. All right, so we want to know, okay, so what fraction of these stars that we've plotted are actually main sequence or are actually red giant branch stars? And so when we put this command length, sorry, this function, this is one of those built-in functions again, because it's green. Len stands for length, and it's going to give us the length of an array. So what is our array color? Let's search for color. Okay, yeah, remember color is our F minus F4 5 something minus F814. So that's the length of our color. So that's all of our stars. And we'd like to print out this statement that says the fraction of stars in the main sequence is, it is in a second, the sum of MS. What is MS? MS was that mask divided by the number of stars. So this is saying the size of our data set divided by the number of stars. So it's just going to give us a fraction. So what is this weirdness in here? This is one of the many ways you can write this as a string and print it out. This uses, this is saying we want to take what is in this format, this number here. Using this command format, it can turn it into a string. And it's saying we want the last 0.3. So everything after the decimal point, we want 3 significant figures. And we want it in the form of an F, a float, meaning not a number like in scientific notation and not an integer like 1. We want 1.000, not 1 times 10 to the 0 or anything like that. We want 1.000 in that format. All right, so let's run it and see what happens. Okay, so we got our fractions. So the number or the fraction of the stars that are on the main sequence is 15%. Well, I guess you can't say fraction. The percentage of stars on the main sequence is 15%. Percentage of stars that are RGB is actually 50%. And then what we've done down here, this is an uncommon syntax in Python. There are several ways to do this. This is from actually a different coding language. So I think whoever coded this spoke another coding language first. This is saying the union of these. And then it's saying not the union. And what the union is all the overlapping things. So if I have an array that's 1, 2, 3, 4, and if I have an array that's 4, 5, 6, the union of those is the number 4 because it's in both. And then this little tilde command says take not the union of those. So we want all the other numbers except for 4. 1, 2, 3, 5, 6, 7. And so it's giving the fraction of stars that are not in there, divided by the number of stars, and that gives the fraction of stars that are not selected. Of course, this excludes the AGBs, so it should be a little bit different. I would not worry about the nuances of this syntax here. Focus more on how to format this in a string. All right, I know we are running up on time. Let's get ourselves prepped for next session with the Doppler shift. And we'll review the Doppler shift again at the beginning of the next session. But Doppler shift is a phenomenon you have all encountered before. Have you ever heard like an annoying motorcycle go by or an ambulance? You know that as it gets closer to you, it goes. That peak in pitch happens as the waves of sound are compressed as they head towards you. Now we call that low frequency when it's and is high frequency. But there's also a correlation there, oh, not a correlation, I'm sorry, a direct relationship with wavelength. So when you're low frequency, you have long wavelengths. When you're high frequency, you have short wavelengths. And this is important for our thinking about light, because indeed this also happens with light. So what redshift is a quantifying how much light is being stretched as something is moving away from us and as something is moving towards us. Because just like the ambulance, when something like a star is emitting light and moves away from us, those wavelengths are going to be stretched out. And even when it's moving towards us, just like the ambulance, those wavelengths are going to be compressed and become shorter and bluer. Because long wavelengths in your rainbow are your redder colors, and shorter wavelengths are blue and violet. But you may have also heard of redshift talked about in a couple other ways. So this is the Doppler shift, redshift. Redshift is always due to movement, but sometimes it stands for other things too. So type 1 here in this GIF is the motion of things relative to each other. So that's like our star moving towards us or away from us in that diagram. In this case, it's lightly scrunched up and blue shifted because moving towards it. There is another type of redshift, though, that happens because space is expanding between 2 points. Now, every point in the universe is expanding. That is what causes our universe to grow. This is a fun aside, but the name Big Bang is kind of a bad name because it makes us think of an explosion when we think about the beginning of our universe. And indeed, our universe didn't explode out from one single point. It was actually born infinite. It was born in one single instant, yes, but instead of exploding outwards like this from one point, it was just born infinite. And it's becoming a bigger infinite every day. And so as space stretches and the universe expands, 2 points, imagine 2 points on a balloon as you blow up a balloon, those 2 points are being stretched away from one another. And so that relative motion also causes it to redshift. And due to like various nuances with the fact that it's expanding at every point on that balloon surface, at every point in our universe, the further something away is, the more that light gets stretched, the more it gets redshifted. And so we can actually relate this redshift term to mean a distance away from us. And then type 3 is that this is not as common. You think about gravitational forces warp the course of light. So yes, it helps us measure the distance of deep space objects, even helps us do things like find exoplanets. But the redshift that we're going to be concerned with today is this Doppler shift that happens between two objects that are just kind of moving normally. Andromeda is close enough to us that it's gravitationally bound to us. So it's not experiencing that shift of the expansion of space between the two of us. Not enough for us to notice. Our gravity is still winning. So all the motion that we see in our redshift, in our Doppler shift, is going to be from the movement of the stars themselves in Andromeda, not from space expanding between us. So that's what we care about the Doppler shift here. Now, the Doppler shift is easy to see when you're thinking about these spectra. Now, what a spectrum is, it is how much light is coming in at each wavelength of light. And an easy way to represent this is as a rainbow. But the notable thing about these black lines here is that these represent some atoms or molecules that are absorbing light. These are called absorption lines. And so if we were imagining this light coming from our own sun, which is probably what this spectrum is, we would be seeing the presence of, for example, hydrogen in our sun, which absorbs certain wavelengths of light and doesn't let them out, which means we have these black lines where we get little to no light. And when we compare where these lines should be with where they actually are, so where they should be is called lambda rest here. That's if we were standing right up close to it. And where we actually see them by the time they arrive to Earth, when they're shifted and stretched and redshifted, that's our lambda nu. So this shift in a spectrum, you can see how these would line up, but don't. That difference gives us a quantity that can tell us how redshifted we are, which can actually do things like, oh, I'm getting ahead of myself. Let's take a look at this slide first. So what we see when we observe a spectrum of a moving star, so this is that a fancier version of this rainbow. This is exactly what we talked about, where we measure how much light is coming in at each wavelength of light. And so we see a lot of light coming in here at 400 nanometers and not so much coming in over here at 680 nanometers. But we see these very distinct absorption lines where something is absorbing the light and stopping it from coming to us. But if instead we saw this spectrum, which we expect to look like this, if we were standing up right next to it, and we see that it's shifted over, we can compare those absorption lines and we can say, hey, this is supposed to be over here at 480 nanometers, but instead it's at 500. And we can use that to tell how fast something is moving away from us. And we do that by using this formula. We take the expected or the rest wavelength of, say, this absorption line here. And then we look at what we actually see for our wavelength. And we can use that to get a velocity. And then C here is the speed of light. So in this case, pay attention to this. We'll repeat this tomorrow. But when the velocity is less than 0, something is moving towards us. And then when the velocity is greater than 0, it's moving away from us and redshifting. blue shifting towards us, red shifting away from us. And then the speed of light, since we're going to be working in units of kilometers, the speed of light is 3 × 10⁵ kilometers per second. So with the time we have, we're going to open up number 4 just to get ourselves oriented to it. So what we're going to be doing in this one is we're going to be using that equation to shift over our given wavelength, our rest wavelength, and we're going to use that to get a new lambda given some velocity. And what we're going to do is we're going to use this equation. So we'll start out tomorrow with plugging in this equation into this function, and we're going to use that to map out the velocities of stars in Andromeda. And you can maybe make some predictions about what you might see. Think about the fact that galaxies rotate, and that we've taken a chunk, if you remember from the paper, a chunk of Andromeda that's just 1/2 of it. So you can think, Andromeda's kind of on its side, it's rotating one way or another. I wonder what we'll see in terms of are our velocities going to be going away from us, or are they going to be coming towards us? All right. So with that, I'll stop my share. We can wrap up, and we'll begin again tomorrow with that notebook. Thank you all for hanging on. I know this is a lot of information all at once. Please revisit those Python notebooks on your own to just work through them and ask plenty of questions in the Slack. We're there to answer them.
Thank you so much, Madeline. We had a request for the slides that you were just showing. Could you post a link to that, to those slides in the Slack channel, please?
Absolutely. I think they're also in the schedule, but if not, we need to get them.
No, they are in the agenda, I believe.
Oh, because I checked them and I didn't see those in particular.
Well, then we'll get them in there for sure.
Okay.
Thank you. And if you could add it to the agenda, that'd be great. Maybe, but I was looking for that particular slide, and maybe I just didn't see that actual slide that you were using.
This is the Star Wars theme stars slide set that Maddie put
No,
together?
this is the other one.
No, it's a different one. Yeah, I've already shared the link to those. That's in the Slack. Aparajita shared that in the Slack, and I put that in the Zoom chat. But this is, that's a different set of slides.
Sorry.
Yeah, those are really dynamic, Madeline. Thank you. Raja?
And so in response to one of the questions, I put a link in the chat. Someone was asking about the completed notebooks. Max was asking about that, and I put a link in the response to it's a, I don't know, is it a direct message? No, it's a, I think it's a general message. So people should see that. I put it's on the, there are a lot of resources on the PyaR website. Maddie, this was terrific. This was really good. We'll have plenty of time to get through notebooks 4, 5, 6. 5 is a very short notebook. So it'll be, I think we're well set up to cover that tomorrow. No issue. I don't think there'll be any issues there at all.
Is there any work we should do tomorrow's session? I would say just go over the notebooks that we got today. That's all you need to do. Refer to the completed notebooks if you have to. And please ask your questions in the Slack channel. There were a lot of questions today, which is great. We love that. Maybe we couldn't get to a few of them. If so, we're sorry. But please feel free to ask them again in the Slack channel. We will get back to you, I promise. It just takes a bit to type out the whole response. Sometimes make sure that we are correct, because it's important for us to know when we don't know something. Okay, anything else? Any other questions?
I wanted to thank. Sorry, go ahead.
Sorry. By the way, Maddie, do you have a link to the annotated version of the paper, of Claire's paper?
There was one that I can send you the PDF. Yeah.
Yes, the PDF. Okay, that will do.
Great. Could you send that to me as well, Madeline, so we can add it to the PyaR resources? Thank you.
Will do.
Raja?
Oh, I was just going to thank all the interns as some are staying up very late at night or getting up very early in the morning to take part in this. So appreciate that. There are folks connected from Hawaii, just 3 hours behind, and there are folks connected from Africa and Asia where it's very late. So thanks everyone for doing this all hours of the day and night.
Absolutely. Thank you so much to all of our interns again, and to our mentors. Of course, Raja, Philip, Aparajita, Madeline, Geronimo, and Lordrick. We didn't get a chance to allow Lordrick to introduce himself. He joined a little bit late after we'd started, but Lordrick has also been here, was here yesterday. I will be sending out a link to the recording sometime later today. You can find it on the Shadow of the Scientist website, but it will be sent to all participants in today's session. All right, we'll see you tomorrow for session 3. Thank you so much. Have a good rest of your morning, afternoon, or evening. Aloha.